Hello, and welcome back to rotation in honors topics in physics. So, wanted to talk a little bit about applications of what we've been learning. So, picture this as a train track, and these are the wheels of a train. So, basically, I took a wheel from the train, and I set it on the track, and I cut the track. So, I'm looking into the cut that I made. So, now the question here is, how do trains steer? Okay, they give you a hint. They do not have a steering wheel. That would be a very boring job on a train because they do not have to steer. They automatically steer, which is kind of interesting. And the way they automatically steer has to do with how these the wheels are tapered. Okay, now there's two ways we could taper the. So sorry for the interruption there. So the trick is how the wheels are tapered. They can taper getting wider on the outside, or they can taper getting wider on the inside. The question is, which one do you think would be more stable to keep the train on the track? So think which one is going to be more stable. All right, and then I'll show you the trick. Now when let's say let's say that the wheels get off-centered a little bit. So here we've got this off-centered. So now I've got the track touching a small diameter of the taper here and a large diameter of the taper here, which means that since these both have the same rotational speed, okay, they're going to have the same rotational speed, but they're not going to have the same tangential speed. So this one is going to travel faster, okay, which means that's going to cause this to go in, okay. And this one right here, so this is traveling faster here, and this is traveling slower here because it's in contact with the smaller diameter, and this is in contact with the larger diameter. Okay, which means that's going to cause this side to come in. Okay, now which of those is going to keep the train on the track? Okay, the one on the right is going to be more stable because this is too far to the left, so it needs to move to the right to be more centered on the track. So they auto-correct with these tapered wheels. So that one would fall off and be anti-stable, and this one would be quite stable, and that's what they use. Another application of what we're talking about is when a car makes a turn, the wheels on the outside of the turn have to travel a greater distance than the wheels on the inside of the turn. Okay, so now they're both the same size. Okay, so I can't change the radial distance. Well, I could put bigger tires on this side, and the car would only be able to turn right. But that's not what we want to do. We have to allow these to spin independently. So this wheel needs to make more rotations than this wheel, and that's accomplished through what's called the differential gear. And I used to have this really cool animation of how a differential gear worked. But I'm pretty sure it's, oh, maybe it will work. Apparently, let me go look. No animation that I could find, for how a differential works. They got rid of it, so. Alright, on to kind of the next topic, which has to do with, centripetal, force and centripetal acceleration. So, would we say that this ball accelerated? Is that ball accelerating? Yeah, sure it is. It's changing velocity. Okay. What causes an object to accelerate? A force. Okay. And what direction is the net force on this? Pushing it to the right. Okay. Now, is this ball accelerating? Okay. Is it changing velocity? Okay. Yes, it is. It's not changing speed. Okay, but it's changing velocity because it's constantly changing direction. Would it require a force to cause this object, this ball, to move like this? Would a force be required? Sure it would be. If it wasn't, it would go in a straight line. Okay, so what direction is that force acting? Okay, it's to the center of the circular path that it's moving along. Okay, so the velocity of an object traveling in a circle constantly changes, even if its speed is constant, because the direction is changing. So if you look, this is the direction of travel in that arrow. Okay, so the direction of travel, and aka velocity, is constantly changing. Therefore, it's accelerating. therefore it needs a force. Okay, so here we've got the tangential velocity marked off in that black arrow. Okay, this blue arrow represents the force that's causing it to travel in a circle. Okay, but it only changes the direction. Okay, not the speed, and that's because it's never in the direction of the tangential velocity or opposite the direction. It's always perpendicular, and if the force is perpendicular to the motion, it doesn't change its energy. Okay, so it doesn't change its velocity. Force and distance have got to be parallel, or at least in some component, in order for there to be work done. Okay, so this inward force that's causing the object to travel in a circle is called the centripetal force. A lot of times abbreviated F sub c for centripetal force. The centripetal force is always perpendicular to the tangential velocity, and it always is pointed to the center of the circle. Okay, the centripetal force does not do work, and that might be a test question. The centripetal force does not do work on an object because it's always perpendicular to the motion. Okay, it doesn't change the velocity; it only changes the direction. Okay, so the centripetal force that we're talking about is not going to get added to our list of normal force, frictional force, force of gravity, force of tension. It's just one of these guys that we've already talked about, causing an object to travel around in a circle. Okay, and that force has got to be constantly pointed to the center of the circle. Okay, how does it know how to change direction constantly? Is it something that's complicated? No. Okay, if I picture me with a string and a ball. Okay, I'm spinning a string, the ball around on a string. Okay, over my head. Okay, and the string constantly is pulling it to the center of the circle. That's just what strings do. They pull in the direction of the string. Okay, and the string is always to the center of the circle. So, yeah, it's not a new force. So, so what type of force is providing the centripetal force? In this scenario here, we've got the Earth traveling around the sun. There's a constant inward force, an attractive force between these two. And the force that's causing that is gravity. Okay, the force of gravity, the attraction between the sun and the Earth, causes the Earth to travel in that circular path. Okay, what about if I had a penny on a record, and the penny was spinning around on the record? Okay, what keeps it traveling in that circular path? What type of force? This is an overhead view, by the way. What type of force would be involved in keeping that penny on there? Okay, and keeping it traveling in a circle? Well, that would be the force of friction. Okay, if there was no friction, the penny would just slide right off. Okay, here's a ride that they used to have at Six Flags. I believe it's no longer there anymore, but it basically was a big washing machine drum in the spin cycle, and they would spin you around on this, and then the floor would fall down, and you would stay stuck to the wall. And the question is, what is providing the centripetal force here? What's keeping you traveling in this circular path going around the circle? Okay, well, that would be the wall. Okay, what type of force would be acting? So the force would be acting through the person towards the axis of rotation. Okay, what kind of force would that be? That'd be a normal force. Okay, friction may prevent you from sliding down. Okay, but it's the normal force which is pointed to the center of the circle, which is keeping you traveling in that circle. Okay, and that normal force is constantly going to be pushing to the inside. Okay. So this is normally when I do a demonstration with the ball, and so I'm going to spin the ball over my head, okay, and then I'm going to let go of the string. I'm not going to cut it. I'm going to let go of the string. And the question is, if there's no gravity, so picture this, we're not in a gravity state, okay, and I let go of the string right here, which path would the ball take? Would it take A, straight line away, B, diagonal, okay, C, a curved path, okay, D, straight path, E and F both curved path, following along the circle and then traveling inward along the circle. So again, there's no gravity here, so ignore that. Okay, so first off, when the string is cut, there's not going to be any forces acting on the ball, which means I can eliminate any path that is shaped how? I can eliminate any path that is curved. So really I've got A, B, and D that are all that are left. Okay. which one will it travel? So it's traveling around in a circle. Will it go A, B, or D? Okay, normally this is when I would do this experiment. And what you would find out is it's D. Okay, it travels the path of D. The reason for that is that that's the direction of the tangential velocity. That's the direction that it was traveling just before the string was cut. And when there's no string, when there's no forces acting on it, it just keeps doing whatever it was doing, and that was its tangential speed. Okay. Okay. Let's skip that. So when you're driving in a car, okay, when you speed up, okay, you feel like you're pushed back into the seat, but really it's the seat that's pushing you forward. Okay, and when you slow down, you kind of go into your seatbelt, and really there's nothing that's throwing you forward. It's just that's your inertia continuing to do what it was doing. And when you make a turn, okay, let's say you make a hard turn, it feels like you're pushed into your seat. On the door on the left if you're driving. And if you make a hard right turn and you're driving, you feel like you're pushed into the door on the left. But really, it's the door that's pushing you to the right so that you can make that turn. And on this spinning ride, okay, you feel like something is pressing you into the wall. Okay, but let's look at the forces that are acting on this girl. Okay, there's gravity down. Okay. There's friction acting up if she's not sliding down. Okay, and then there's the normal force that is pushing her into the center of the circle, that's causing her to travel in the circle. So these are my three forces. Okay, there is no outward force that is pushing you into the wall. Okay, that is just due to your inertia trying to go straight, and the wall having to push on you to make the turn. Okay. So again, there's only an inward force. Okay, there's no outward directed force. Some people call that the centrifugal force. Okay, that's not a real force. That's a made up force. There's no force that's doing that. It's just the result of you trying to go straight and the object trying to pull you in. You feel like you're being pushed out. Okay, so the only centripetal force inward, no centrifugal force outward. Okay, so let's say we've got an overhead view of a car going around a circular track. Okay, what's causing the so this is a flat track on Earth where he's not actually traveling up and doing the loop-de-loop. So what force is providing the centripetal force here? Okay, what's keeping it on the track? Okay, that would be friction. Okay, now if that friction is lost, okay, it just keeps doing whatever it was doing. So it was traveling downward, downward, quote unquote, according to this picture. So it's just going to continue to travel downward and not make the circular path. Okay, so again, let's skip that. Okay, let's skip that. Again, you feel like you're being pressed into the wall of a rotating circular ride, but there's nothing that's pushing you into the wall, pushing you away from the center of the circle, pushing you outward. It's just the wall is pushing you inward, and so it feels kind of opposite what's going on. And that's kind of a recurring theme with how forces feel versus how they are. So the faster an object goes around in a circle, the more centripetal force is needed to keep it in that circle. Okay, so if you're thinking back to an elevator, when do you feel? When the elevator starts moving upwards and is accelerating upward, how do you feel? Okay, well, the elevator pushes you up, so you feel like you're being pulled down. Okay, so keep that in mind when we talk about this. So a lot of times, or in a lot of movies, they portrayed spaceships as having a rotating portion of the spaceship, and so this is my spaceship, and we're rotating in outer space, and so we're traveling in a circle, which means there's a centripetal force and a tangential velocity and all that stuff. Okay, so so we're on the floor, the quote unquote floor of the spaceship. So which way is the normal force acting on my feet? Okay. It's acting upwards through my body. Okay, so towards the center of the circle. So from my perspective, that force is always up, though. Okay, so the floor is constantly pushing me up. However, what it feels like, okay, is that something is pulling me down. Okay, and so by spinning this spaceship, we were able to create artificial gravity with the rotation. Okay, so all things considered, which one will need more centripetal force? The left or the right? Okay, the one on the right, because it has a greater rotational speed and a greater linear speed as well. Okay, so how could I increase the artificial gravity on my space station? Okay, I could change the rate of rotation, which would mean more centripetal force, which would mean more artificial gravity. Oh man, can you just feel yourself being pulled down to the ground in the spaceship rotating this fast? I can. I feel like I'm being drugged down. Okay, so let's take a look at these now. Here we've got a double-decker spaceship. So I've got 2 floors. Which one has the greater rotational speed? This is like our 2 pennies on a record. Okay. Well, they both have the same rotational speed because they're both making one rotation in the same amount of time. Okay. Compare their tangential speeds. Okay. Well, the one on the outside is going to have a greater tangential speed because there's a greater radial distance. Or you can think about it as it's traveling a greater circumference in the same amount of time, so therefore it's got to be moving faster. Okay. So who's going to feel more artificial gravity, the person on the inside or the person on the outside? Well, the person on the outside who's spinning, who's got a greater tangential speed, is going to have a greater artificial gravity. So let's say we've got 2 pennies on a record, and similar to our two astronauts, and I were to give this a spin. Which penny would fly off faster? Okay. Well, the penny that would fly off faster is the penny that would be traveling faster, which would be this outward penny, this outer penny. So, because it has a greater tangential velocity, it's going to need more centripetal force. Okay, so just the right amount of force is needed for something to travel around in a circle. In a lot of cases, this is just kind of naturally is matched. So when I swing a ball on a string faster, the string pulls back harder to match the centripetal force needed until the string breaks. So if you supply just the right amount of centripetal force, you travel in a circle. Okay, if there's too much centripetal force, you'll travel inward, and if there's not enough centripetal force, you'll travel outward. Okay, for a penny that's spinning around on a circle, okay, the net force is the centripetal force. That's something that's probably worth making a note of. So this is called uniform circular motion, UCM, uniform circular motion. And when an object is in uniform circular motion, which basically just means traveling around at a constant speed, the net force is the centripetal force. The force that's left over is the centripetal force. Okay. So spinning a ball around in a vertical circle. So now this is not an overhead view. This is just like normal view where it's going up and going down and then going back up and then going back down. Okay. So the force of tension changes in the string depending on where we're at in this circle. Okay. So at the bottom of the swing, okay, gravity is pulling down. Okay. And let's say we need 5 newtons of centripetal force. That's our magic number for centripetal force. And if gravity is pulling down with 3 newtons of force, the tension is going to be being pulled up. Okay, how much force is required tension to give me a leftover force of 5 newtons? Well, if I have 3 down, okay, and I want 5 up left over, I've got to have 8. I've got to have 8 forces, 8 force of tension newtons. 8 force of tension, 8 newtons of tension, and that'd give, when I subtract my 3, that'd give me my 5 left over going up. Okay, so be able to do this. Basically, you're just going to add or subtract the force of gravity and the centripetal force. It's not a big deal. Okay, at the top, Okay, gravity is acting in the direction. We want our centripetal force to be down because that's the center of the circle. Okay, so our net force should be 5 newtons down. Gravity still is 3 newtons from before, and it's still 3 newtons down. Okay, but the difference is I want my force to be down. So what does my force of tension have to be at the top to give me that 5 newtons down? Well, it just has to be 2 newtons here. Okay, all right. Another example along those lines, again, there'll probably be something along the lines that's on a test. Let's say a ball on a string needs 4 newtons of centripetal force. The ball has a weight of 3 newtons. What's the tension in the string at the top and bottom of the vertical circle? Okay. Well, where is it going to be the greatest? It's going to be the greatest at the top or the bottom, the force of tension. When do you feel the heaviest on a spinning roller coaster ride? Okay, at the top or the bottom? Okay, you feel the heaviest at the bottom. So you're going to need more tension at the bottom than you do at the top. Okay, so let's look at the top first. So we need we need 4 newtons of centripetal force. Sorry, let's modify that problem. Let's say it needs 5 newtons of centripetal force, and the ball has a weight of 4 newtons. Okay. So at the very top, I need 5 newtons of centripetal force down. Now I need that to be my net force. Okay, I've already got 4 newtons of gravity. Okay, so I need the rest of that to be made up by the force of tension to give me 5 newtons. Okay, so putting that in an equation, Fc equals 4 plus Ft. Okay, so 5 plus 4 equals Ft. Ft equals 1. Okay, so my 1 newton here gives me 5 newtons total. Okay, so basically I subtracted them. So at the top you subtract. Okay, at the bottom, okay, so I need 5 newtons of net force up. Okay, and I've got 4 newtons down. And what is this going to have to be when I subtract 4 to give me 5? Okay, well that's going to be 9. Okay, so at the bottom it would be 9. So at the bottom you add them. So pretty straightforward. Okay. All right. Now let's say I swung that ball lower and lower and slower and slower. I mean, let's say that the ball only needs 4 newton ball only needs 4 newtons of centripetal force because I swung it slower. That means that the string is going to go tensionless at the very top. It'll be limp at the very top. Okay, but it'll still make it around the circle. Let's say that at the very top, my 4 newton ball only needs 3 newtons of centripetal force. Well, at this point, I'm going to have more centripetal downward force in my 4 newtons than I need to make it around the circle because I'm going so slow. Okay, and I'm not going to travel around that circle. I'm going to fall inward on that circle, so the string will go slack, and the ball will come towards my hand some. Okay, the slowest speed that an object can make a vertical loop is when the centripetal force is equal to its weight. Okay, so normally I have a cup of water that I would swing around and swing it slower and slower and slower, reducing the amount of centripetal force, and eventually the string goes slack, and the water, I usually try to keep it in the cup, but not always. Okay, so this is the Highland Fling. I don't know what it's called anymore, but you've got a roller coaster that's a spinning roller coaster, and it starts off flat, and then it goes into a vertical circle. And so you feel very, very heavy when you're at the bottom, and then you feel lighter when you're at the top. Very similar to the strings. If this was a string were to hold you, the string tension would be greatest at the bottom, and it'd be the lightest at the top. Okay. Okay. Now, if you spin the slowest that you can possibly go, where the centripetal force is equal to your weight, okay, at the very top, okay, there's no force needed. There's no tension force or normal force needed. You're in free fall, and you would feel weightless. And at the bottom, though, you feel very heavy. Okay, that is that for that. Sorry about the longer notes today, but it is what it is. So have a good day. So do worksheet 7-4, and I'm not sure why I've got these on here. I'll have to look at